Hi, everybody. It's Professor Mitchell. We're continuing today with Chapter 2 on polynomial and rational functions. And today we're going to be talking about Section 2.5, which is zeros of polynomial functions. So here are the objectives of this section. We're going to use the rational zero theorem to find possible rational zeros. And then we'll find zeros of a polynomial function, solve polynomial equations, use the linear factorization theorem to find polynomials with given zeros, and finally we'll use Descartes' rule of signs. All right, so here is yet another one of those things that's a lot simpler than it sounds. So if f of x is a polynomial, that's how I'm going to read all of this right here. That just says f of x is a polynomial with integer coefficients. And if the fraction p over q is a rational zero of f, then p must be a factor of the constant term, a sub 0, and q must be a factor of the leading coefficient, a sub n. So you'll get a better idea of what that means in the examples. Again, it's a lot simpler than it sounds. So we're going to use the rational zero theorem to list all possible rational zeros of f of x equals 4x to the 5th plus 12x to the 4th minus x minus 3. So right now we're not going to determine which ones of those are actual zeros. We're just going to list all of the possibilities. So the way that works is you note the constant term -3 and the leading coefficient 4. The factors of -3, and you can think of it as 3 if you want for this, would be plus or minus 1 and plus or minus 3, right? 3 is a prime number. Its factors are 1 and 3. So you just have to throw in the negatives. We're looking for all integer factors. So that includes negatives. And the factors of the leading coefficient 4 are plus or minus 1, plus or minus 2, and plus or minus 4. All right, so remember that any rational zero of this polynomial, its numerator would have to be a factor of -3, and its denominator would have to be a factor of 4. So this is exactly the same way I write it when I'm writing it on a piece of paper or on a whiteboard. The factors of -3 are plus or minus 1, plus or minus 3. The factors of 4 are plus or minus 1, plus or minus 2, plus or minus 4. So when you put each of the numbers in the numerator over each of the numbers in the denominator, you get all of these numbers here. So 1 over 1 is 1, 3 over 1 is 3, 1 over 2 is 1/2, 3 over 2 is 3/2, 1 over 4 is 1/4, 3 over 4 is 3/4. So this polynomial has a total of 12 possible rational zeros. I believe we know from the last section that the maximum number of zeros it actually has is 5. So clearly not all of these are actual zeros, but these are all the possibilities, okay? So where we're going with this is that gives us a really good, when we start looking for actual zeros, we will work from this list. All right, and that's what we're going to do right now. We're going to find all zeros of the polynomial x cubed plus x squared minus 5x minus 2. All right, so we begin by listing all possible rational zeros. All right, remember the possible rational zeros are the factors of the constant term divided by the factors of the leading coefficient. I'm very happy that there are not 12 possible rational zeros for this one. There are only 4 possible. All right, the possible rational zeros are plus or minus 1, plus or minus 2. So what we're going to do now is we're going to use the factor theorem from the last section to determine which ones of these are actual zeros. And we're going to do that using synthetic division. All right, so we just take these one at a time, and you can start wherever you want. I would probably start with 1 because that's the easiest, but they started with -2. So here they are testing to see if -2 is a 0 of this polynomial. Remember, the factor theorem says that -2 is a 0 if and only if x plus 2 is a factor. All right. So a quick review of synthetic division. You bring down the 1, and then -2 times 1 is -2. 1 plus -2 is -1. -2 times -1 is +2. -5 plus 2 is -3. -2 times -3 is 6. -2 plus 6 is 4. So when this polynomial is divided by x plus 2, the remainder is 4, which means that x plus 2 is not a factor of this polynomial, which means that -2 is not a 0. Similarly, -1 is not a 0, and you can see that synthetic division over here. All right, so we know -2 doesn't work, we know -1 doesn't work. So we'll continue by testing 2 and 1. 1 doesn't work, has a remainder of -5. However, 2 works, see? The remainder is 0. So remember how to read this synthetic division. When you divide this polynomial by x minus 2, the remainder is 0. And the quotient is x squared plus 3x plus 1. So that's the other factor that goes with the factor x minus 2. So what we know at this point is that x cubed plus x squared minus 5x minus 2 factors into these two polynomials. So now we will solve the quadratic equation x squared plus 3x plus 1 equals 0 to figure out what are the remaining zeros. And we'll do that by using the quadratic formula. So you remember how that works. Using the quadratic formula, you get that the other two zeros of this polynomial are -3 plus square root of 5 all over 2 and -3 minus square root of 5 all over 2. So the full complete list of zeros of the polynomial x cubed plus x squared minus 5x minus 2 is right here. One of the zeros is 2, and the other two are -3 plus or minus the square root of 5 all over 2. Okay, next we have some properties of roots of polynomial equations. First, if a polynomial equation is of degree n, then counting multiple roots separately, the equation has exactly n roots. Now, what they mean by counting multiple roots separately, let's say that let's take something very simple. Let's say we had x minus 2 squared equals 0. X minus 2 squared equals 0. That is a degree 2 equation. So what they, and it has one distinct 0, which is 2, but the multiplicity of that root is 2. All right, so what they mean by counting multiple roots separately, if you count the 2 twice, it does have 2 roots. So hopefully that makes sense. All right, this one's going to come in handy in a little bit. If a plus bi is a root of a polynomial equation with real coefficients, all right, a plus bi being a complex number, then the imaginary number a minus bi is also a root. So in other words, imaginary roots, if they exist, occur in conjugate pairs. So I will show you in a little bit exactly where I'm going to use that. All right, so this example is kind of similar to the last one. This might be a good one for you to pause the video and try this one. We're going to solve the equation x to the 4th minus 6x to the 3rd plus 22x squared minus 30x plus 13 equals 0. All right, so we will start, just like last time, by listing all of our possible rational roots. And those would be plus or minus 1, plus or minus 13. So now we'll start using synthetic division to test each of those possible rational zeros. All right, so if we start with -1, that doesn't work. This polynomial divided by x plus 1 has a remainder of 72. However, if you divide by x minus 1, right here, that does leave a remainder of 0. Okay, so that means that this polynomial factors into x minus 1 times x cubed minus 5x squared plus 17x minus 13. Now, basically, you have to continue this process until you get something that is degree 2, because, of course, anything that's degree 2 can be solved using the quadratic formula. Okay? But I don't know any other way to find zeros of a third degree polynomial except for the way that we've just been talking about. So we're going to continue this process and try to find a zero of this third degree polynomial. Now, we've already checked, okay, so this is just a continuation or a repetition of what it already said. So if you list your possible rational roots, you get the same ones that we got for the big polynomial. Now remember, we already tested -1 with the big polynomial. Since -1 is not a zero of the big polynomial, it can't be a zero of this thing. All right, think about why that is. All right, so we won't bother testing -1, but we will test 1. I know we already tested it and we got, you know, the x minus 1 to factor out. But it could be that x minus 1 will factor again out of the third degree polynomial. And in fact, it does. See that? If I divide this third degree polynomial by x minus 1, I get a remainder of 0. Okay. So what we have at this point, the factored form of the original fourth degree polynomial, we got that first x minus 1 in the first step. And now we've gotten out another x minus 1, and we are left with this quadratic factor, and we'll figure out the zeros of that by using quadratic formula. And here it is. So when you use the quadratic formula to solve this quadratic equation, you get that the two additional zeros beyond the 1 that we already found, which is called a double root because it has multiplicity 2. Those imaginary zeros are 2 plus or minus 3i. So the solution set of the original equation, notice they've listed the 1 twice because it has multiplicity 2. They're just trying to emphasize that this fourth degree equation does have 4 roots if you count the 1 twice. All right, and that brings us to the fundamental theorem of algebra. If f of x is a polynomial of degree n, where n is greater than or equal to 1, then the equation f of x equals 0 has at least one complex root. Now, the way I always explain what's so important about this, you know, think about different number sets that you've encountered ever since elementary school, right? The first number set that you worked with was the counting numbers, 1, 2, 3, 4, 5, 6. And then you probably opened it up to, I guess, 0 would have come next, and then fractions, and then negative numbers. And then at some point you learned about real numbers, right? Decimals that cannot be written as fractions. And then at some point, maybe even in this course, you learned about complex numbers. So the question could be like, where does it end? All right. When are they going to stop making these sets of numbers bigger and bigger and bigger? Well, what the fundamental theorem of algebra basically says is we're done. complex numbers do everything that we could ever possibly want. Okay. All right. And now we have the linear factorization theorem. So if f of x is a polynomial with degree greater than or equal to 1, and the leading coefficient is not 0, I don't think they necessarily needed to say that, but anyway, then f of x can theoretically be factored like this, where you have your leading coefficient sitting out front, and then you have a set of n factors where these numbers c1, c2, blah, 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 up to c sub n are complex numbers, and they are not necessarily distinct, right? Some of these complex zeros might have multiplicity greater than 1, all right? So it's just saying that you can factor any polynomial completely using complex numbers. Now, when I first started saying this, I said theoretically, because for some polynomials, it is literally impossible to find all of these factors, all right? And that's a topic for a much more advanced math class. But anyway, they do exist, all right? So here's how we're going to use the linear factorization theorem. And I actually have 2 examples of this. I'm saving one for you to try next. We want to find a 3rd degree polynomial function, f of x, with real coefficients that has 6 and -5 plus 2i as zeros, and such that f of 2 is equal to -636. So I'm going to work this one out on the tablet. And I've already got what I need about this problem written down. Okay, so the first thing I want to point out to you, since -5 plus 2i is a 0 of this mystery polynomial, then that must mean that so is -5 minus 2i. Remember, a few slides back, we had that property that said that if a polynomial with real coefficients, if it has an imaginary 0, then the conjugate of that imaginary 0 also has to be a 0. Okay. So even though they only gave me 2 of the zeros, I know what the 3rd one has to be. Okay, so now I'm ready to start figuring out what this polynomial is. I think I will switch to a thinner pen here. All right, so the linear factorization theorem says that this polynomial will have the form f of x equals a sub n times x minus 6. That would be the factor that gives you the 6. Another factor would be x minus -5 plus 2i. That would give you the 0, -5 plus 2i. And then the other factor would have to be x minus -5 minus 2i. All right, so unfortunately, what I have to do next is multiply all that out. All right, I want to show you a little shortcut for multiplying these 2 right here. Okay, what I'm going to do is I'm going to do a little bit of clever regrouping. So instead of writing this second factor the way it's written, I am going to write it as, I'm going to put the parentheses around the first 2 terms, and it's going to look like this, x plus 5, and then this is going to be minus 2i, right? Notice that if I were to distribute this negative over these two terms and drop the inside parentheses, it would look like x plus 5 minus 2i. So I might as well put the parentheses around the x plus 5, and I have a good reason for doing that, by the way, which you'll see in the next step. And then I'm going to do the same thing to this other factor. I'm going to write it as x plus 5 plus 2i. Right? If I were to distribute this one, right, and drop the inside parentheses, that would become x plus 5 plus 2i. I'm putting the parentheses around the x plus 5. Now, the reason I wanted to group them like this is because if you look at these two factors right here, those two factors are something special. This one here has the form a minus b. This one here has the form a plus b. All right, so I know an easy way to multiply an a minus b times an a plus b. Right, that's a difference of 2 squares. So, of course, that multiplies into an a squared minus b squared. So that's going to look like x plus 5 squared minus 4i squared. We'll just write it like that for now. All right. See, this isn't too bad. Okay, now that thing should not be too difficult to clean up. All right, when you multiply out x plus 5 squared, you get x squared plus 10x plus 25, right? And then remember that 4i squared is 4 times negative 1. So that's going to be a plus 4. All right, and I think maybe the thing to do is to continue this up here. Oh, I got rid of one piece of information that I haven't used yet, but I'm pretty sure I remember what that says. All right. It's a little bit like writing on a real whiteboard. Okay, sometimes I have to erase the beginning of the problem to write the end of the problem. Okay, so we have a sub n. You know what, let me put an f of x here. F of x equals a sub n times x minus 6 times x squared plus 10x plus 29. All right. All right, full disclosure, I had a little mathematical malfunction here, so I'm starting back at this step. So I was just about to multiply these two factors together. So here's how I'm going to do that. X times x squared is x cubed, and that's the only thing that's going to give me a degree 3 term. However, there are two sets of terms that are going to give me degree 2. And those are negative 6 times x squared and also x times 10x. Negative 6x squared plus 10x squared is plus 4x squared. There are also two sets of terms that are going to give me an x term. And those are, let's see, negative 6 times 10x and x times 29. Negative 60x plus 29x is negative 31x. And then the only constant term is going to come from negative 6 times 29, which is negative 174. All right, we're almost done. So here's where I'm going to use the fact that f of 2 equals negative 636. Remember, that was stated in the original problem. I'm going to use that to find the leading coefficient. And the way that I'm going to do that is I'm going to say, on the one hand, f of 2 equals negative 636. But on the other hand, f of 2 is equal to what I get if I plug 2 into this polynomial. So that would be a sub n times 2 cubed plus 4 times 2 squared minus 31 times 2 minus 174. So now let's see if we can do that math. 2 cubed is 8. 2 squared is 4. 4 times 4 is 16. Minus 62. 24 minus 62 is negative 38. Negative 38 minus 174 is negative 212. All right. So now I think we know what a sub n is. If I divide both sides of this by negative 212, that means that a sub n is equal to 3. All right, so mystery solved. This polynomial that has all the properties stated at the beginning is f of x equals 3 times x cubed plus 4x squared minus 31x minus 174, aka 3x cubed plus 12x squared minus 93x minus 522. All right, so those problems, I will admit, are a little involved, and I think they take a little bit of practice. So what I would like to do now is go back to the slides and have you try this one. Find a third-degree polynomial function, f of x, with real coefficients that has negative 3 and I as zeros, and such that f of 1 is equal to 8. So please go ahead and pause the video and try to work that out. And then when you're finished, come back and we'll compare notes. All right, here we go. So first of all, because I is a 0 and the polynomial has real coefficients, the conjugate negative I must also be a 0. So using the linear factorization theorem, this polynomial has to have the form f of x equals a sub n times x plus 3 times x minus I times x plus I. And when you multiply those all together, you should get x cubed plus 3x squared plus x plus 3. So now we will find our mystery leading coefficient. So on the one hand, f of 1 is equal to 8, but on the other hand, f of 1 is equal to a sub n times 1 cubed plus 3 times 1 squared plus 1 plus 3. And you work that out, it turns out a sub n is equal to 1 this time. So this polynomial must be f of x equals x cubed plus 3x squared plus x plus 3. All right, and that brings us to Descartes' rule of signs. Descartes' rule of signs says that if f of x is a polynomial with real coefficients, then the number of positive real zeros of f is either the same as the number of sign changes of f, or it's less than the number of sign changes of f by a positive even integer, all right? And so what that implies is that if f of x has only one variation in sign, in other words, one sign change, then f must have exactly one positive real zero. Okay. And then the number of negative real zeros of f is either the same as the number of sign changes in f at opposite x. See, take the polynomial f of x, and it has certain positive real zeros. Let's say 1, 3, and 5 are positive real zeros of f of x. The negative real zeros of f at opposite x would then be -1, -3, -5. So you figure out everything you need to know about negative real zeros by looking at the polynomial f at opposite x. So again, the number of negative real zeros of f is either the same as the number of sign changes in the polynomial f at opposite x, or it's less than the number of sign changes in f at opposite x by a positive even integer. And again, if f at opposite x has only one variation in sign, then f must have exactly one negative real zero. All right, so let's see how that works. We're going to determine the possible number of positive and negative real zeros of f of x equals x to the fourth minus 14x cubed plus 71x squared minus 154x plus 120. So to find possibilities for positive real zeros, we're going to count the number of sign changes in the equation for f of x. Now, what they mean by sign changes is if you go from one term to the next, see if the term changes sign. So in this case, there is a sign change here because it goes from positive to negative. There's a sign change here because it goes from negative to positive. There's a sign change here because it goes from positive to negative. And there's a sign change here because it goes from negative to positive. So that is 1, 2, 3, 4 sign changes, which means that the number of positive real zeros of f is either 4, 2, or 0. So you take the number of sign changes and then count down by 2s, all right? So either 4, 2, or 0. All right, and then for negative real zeros, we'll look at the polynomial f at opposite x. So when you replace x with opposite x, you get x to the fourth plus 14x cubed plus 71x squared plus 154x plus 120. There are no sign changes, which means that f has no negative real roots. All right, it has either 4, 2, or 0 positive real roots, or zeros, but it has no negative real zeros. They really should have said zeros there. All right, and that's going to do it for section 2.5 this was, right? All right, so we'll see you next time.